speaker, who's Darren Budd, and Darren is going to talk on the value chain implications when developing a post-fossil world. The floor is yours, Darren.
Hopefully, Tim, you can see my slides.
Yes, can definitely.
And some of this will overlap with, so welcome everyone, with what Jeremy said. So I presented with Jeremy before, and obviously the challenges that Shell have, also the challenges that the BASF have in terms of going in our industry. So a bit like, move to the next slide. Hopefully you can see this. Okay, so as with Shell, in terms of we're remiss in terms of our legal department and our corporate, saying we have to put up a corporate slide to start with. So apologise for everybody, just put an overview of who BASF is in terms of as a global company, in terms of and the important bit is, which I'll come back to, is the second one up from the bottom, is we have in terms of our where our production sites are, and that value chain implications in terms of where we have our what we call our 6 Verbund sites, and they are the fully integrated production sites. And on top of that, we have a further 239, 240 production sites worldwide, which then are much smaller. But it's the Verbund sites which where the value chain implications are. And, so we'll come back to that in terms of where we sit. And our reach is global. So we have 2 Verbund sites in Europe, 2 in the US, 2 in Asia, and there is a 7th one going up in Southwest China. So just in terms of, as we talk to that, but just as we move to that, and like Shell, who have their target of net zero by 2050, BASF have also targeted 2050 as net zero, and to have a 25% reduction of CO2 by 2030. And these are big challenges to get there, and some of the processes that we're working with. So our production sites, like the Verbund sites, if we take our central headquarters, we've been there for over 150 years, 158 years, in terms of actually how do you change that from the fossil fuel into other feedstocks, and the challenges that we have that. So when we look into this in terms of, and I just wanted to come back to start with this in terms of chemistry and the chemical industry, and I look about the history, and chemistry has always adapted as we go through, and it adapts to the raw material changes that we've had. So in terms of that pre-industrial, what we had in terms of soap from soda ash, in terms of potash for burning plant, and then as we moved into the early industrial chemistry in terms of coal, as we were making then ammonia from synthesis, and we're making ammonia and hydrogen today from different sources. And then in terms of the post-war, the crude oil, as we moved into the fossil fuels that we have today, and then moving where we are now in terms of natural gas, and then what do we want for the future? And we're talking today about in terms of those changes away from fossil fuels into renewables, and that how do we then hydrogen, other carbon resources in terms of renewable, those energy transitions that Jeremy talked about, and then the nitrogen fixation, and which are the right technologies. And I think Jeremy summed it up at the end, is actually how do we know we're on the right path for this? And so like Shell, BASF is investing in many different technologies because we don't know which one's going to be the winner in these energy transitions and defossilization. So there's a lot of work going in at early stage research to see how do we get to net zero by 2050, and which are the technologies that are going to be there. And I think that's that adaptation and adaptability to the raw material changes. The chemical industry has always gone through it, as you've seen here, and that's the last 150, 200 years, and we'll continue to go through it in terms of adapt to meet the requirements that industry wants. And why have we done that? As you see, we're here in terms of synthetic indigo dye, which was the founding of BASF, right through, and that's the different chemistries that I talked about before in terms of the dyes, the fertilizers, the plastics, healthcare, and moving into different system technologies. And how do we move away from fossil carbon into maybe renewable carbon? And how do we then meet the challenges that we've got? So we have 8 billion people on the planet, but it's a case of how do we feed them, how do we clothe them, how do we make sure they have the clean water, how do they have everything to live in the world today, but also meeting the environmental challenges that we have and using the chemistry to do that. And that's a really, really big challenge. And what I wanted to show is this as the everyday problem. So here we have a clean liquid, which contains a surfactant, hydrophobic tail, hydrophilic head group. And where does that come from? What are the processes that we have that comes from, and the challenges that we have to meet in our supply chain? And so those surfactants are sold via highly complex value chains that we have today. And you see here crude oil, natural gas. And they go through the changes we make in terms of naphtha, ethane, right through to ethylene, propylene, and as we see, right the way through up the complex value chains that we have in our production sites. And that's good. And you say, well, how do we replace those? Actually, it is quite difficult because these are long-term, efficient production sites that we need to then say, how do we then replace the crude oil? How do we replace those value chains across the industry to meet the demands? And actually, it's okay where we do the fermentation technology, but how do you scale that up? And that is a really big challenge. So one of the areas we looked at is those alternative renewable chains. So this is what we call our chemistry. And on the right, you've got the fossils, the crude oil, the natural gas that comes into the bottom to make the toolbox into and the products we have every day. And then we've said, okay, we need to move away, but where can we build those value chains that meet the requirements? And so we have then looked at renewables, and just as we'll move on to other things, but on the renewable side is, okay, we've got the carbohydrates, the proteins, the triglycerides, and actually they're good, we can replace, but can you do it at volume? And actually, when you're looking at that, and one of the things is those palm oil, but other renewable resources, they have their own challenges. These are natural products, and they need to prove the efficiency. So can you make these processes as efficient as the fossil fuel that we have today? And they're the challenges. So to meet all of those in terms of the conservation, the traceability, making sure that we don't take away land that we need for food, in terms of how do you transport it, how do you protect the environment. And so these are all challenges that we have in terms of the defossilization within the chemical industry that we can meet. So our processes, as we showed in one of the first slides, have been built up over 150, 200 years, and very efficient supply chains. And now we've got to say, actually, how do we take that apart, or how do we then make sure that we can meet the requirements of the world, but also on a sustainable way in terms of, and actually at a cost that people can afford. And this is the three-legged stool. So one is the environment, so we make sure we protect the environment. The second one is the social aspect, so the people. And four is actually we still need to make money to reinvest for the new technologies. So those three areas have to be filled. And if one of them, those legs of the stool, is not fulfilled, then we're not going to make those processes. So from a BSF perspective, in terms of into our Verbund sites, we have it in terms of how do we replace? So in terms of, you've got the four big areas in terms of mobility, energy, waste, nutrition that feed into our processes. And at the top, you've got our traditional in terms of crude oil, natural gas, coal, and how do we then move away? So because they make the chemicals that we have today, can you replace them with the products that I said before, so the plant oil, the cornstarch, but actually then are you taking that away, that natural, those materials away from the food chain? And can you then build in terms of processes, in terms of whether it's fermentation or other oleochemicals, in terms of to meet the requirements of the chemical industry? So these are challenges that have to be built. So we have to make sure that, one, those supply chains, and then if you're putting in terms of plant oil into your products, are you getting a consistency of those products in terms of, can we have new fermentation processes? And an example in terms of on fermentation is we built a bioacrylamide plant at our site in the UK. That was a 25-year changeover from the acrylamide that we had into bioacrylamide. It started at a university in the UK, and it took 25 years to actually get up to full-scale production. And we can't afford to wait that long. through these new value chains. So we have to be faster, we have to spend more money on it, and we have to then get our processes as efficient as the current chemical ones that we're using today. So some of the areas we're working on in terms of, and this, everybody is looking at these areas. So waste is a big one. So defossilization, so looking at municipal or industrial waste, how do you collect it? So we're working with the big waste companies in terms of how do you collect it? How do you sort it? What is the regulation behind that? So, and that is a big one in terms of, and where is the value? So people are saying waste is the new oil in terms of the cost. So a lot of people are looking into the waste and saying, what can we do with it? Can we then use it as a pre-treatment? Can we mechanically recycle it and bring it back into the market? Do we, Jeremy said, in terms of pyrolysis, to get the pyrolysis oil and the gas, or can we, if we have to incinerate it, which then, from a UK perspective, by 2028, plastics cannot be incinerated anymore, so you have to then find other ways of recycling. Can we take the CO2 from those processes that meets our requirements and demands? So in terms of all of these come into ways of finding new novel materials, but also replacement materials for virgin fossil fuels. And it's then working with the technologies and developing those technologies at speed, whether it's in-house or at universities or partners working with the likes of Shell and along the value chain with the waste companies, to make sure that we can meet the requirements that we have to fill our plants, that we can then provide the products to customers at a price that can be afforded. And this is the whole issue we have on that value chain, is do we have enough material, raw material, to replace what we have today? And do we have it in the right places? And is it at the right price? Because at the end of the day, cost is paramount to have this. So can we develop the technologies at a cost where we can work together? So whether that's wind power, solar to produce the electrons to run our plants, in terms of to make hydrogen or ammonia going forward, green hydrogen into our processes. And here, in terms of those renewable energies that feed into our sites, in terms of to produce the hydrogen, to produce the chemical feedstocks, and it's a real challenge. And one of the, as I talked about before, the Bhavin site. So when you're looking at producing these chemicals, and Jeremy talked about the pyrolysis, there's not enough pyrolysis oil on the market to feed everybody's requirements. So Shell is looking for it, BASF is looking for it, everybody is looking for it to replace some of the virgin materials. And in terms of scale, if you want to see then scale of this is the site of our site in Germany. So this is our biggest fully integrated production site here. So it's inefficient. So it's ultimately efficient. So it sits 7 kilometers along the Rhine. It's 2 kilometers at its widest point, and it's fully utilized. The land is fully utilized that we have here. So if you want to put a new production site, you have to then tear something down, and everything is integrated. And the reason why it's verbund is that the raw materials from one that goes into one site and makes a product, the byproducts that will go into another unit to make a further product, and it feeds all the way through the site to make the final products that come out to feed our customers. And this is where the complication is. So if you've got a 1 million ton a year steam cracker, how do you replace that 1 million tons with renewable resources into the value chain? And that's the difficulty that we have, and the challenges we have is you have to then have enough energy in that steam cracker. So can we replace the natural gas that's used to burn and crack the naphtha? And then do you have enough renewable carbon that can go into the steam cracker that can make our products to fulfill our requirements at a cost that we can supply into the market? So these are all the challenges that we have, and we have to find new novel processes, whether it's from wind power in terms of for the electrons to make hydrogen, green hydrogen into ammonia that can be then used for our products, or is it from pyrolysis oil, or in terms of projects that we have like Flutichem in the UK, where we're taking waste CO2 and working with a number of partners, which is the downstream or the upstream industries, so the likes of Tata for the CO2, the paper companies for the CO2, working with Johnson Matthey for technology, Croda, BASF, right through to make the chemicals for the likes of Unilever, Procter & Gamble to make their cleaning liquids. So we have a whole project in the UK looking at, can we utilize that value chain to make new chemicals from existing CO2? And that's a challenge we have today. So this is a multi-partner project, which is funded by UKRI, to see where is that value chain. And we're all taking various steps in that to say, how do we get from where we have today in terms of fossil carbon right through to renewable chemicals? And then how do we scale it up? So it's okay finding the process, but then how do we capture that CO2? How do we transport it? What do we need in terms of the processes to make sure that we can supply plants like this one in Ludwigshafen to make the chemicals that we need today and the building blocks? And then as an example to show as an overlay how big that site is, this is it mirrored on London. So if you put Ludwigshafen into London and where it sits in terms of the issues in terms of supplying those chemicals or renewable chemicals into that site, this is what you would need to fill. And we have 6 of these around the world and a 7th one being built. So you can see the issues that we have, whether it's through biofermentation, whether it's through chemical pyrolysis or any other sort. It's how do we have enough materials that we can feed an efficient production site to meet the demands of today? And they're the challenges we have between now and 2050 to make sure that we can get to net zero. And then I'll leave you with our strapline is we create chemistry for a sustainable future. And we go back to what we had before in terms of all of our 158-year history is looking at that. How do we use chemistry today to meet the demands that we have? How do we have efficient processes and move away from those chemicals and develop new materials, new processes to meet the world's requirements?
Thank you very much, Darren. That was an excellent talk. Described succinctly the resilience of the chemical industry in the past, and also illustrated the resilience of the chemical industry, in particular BASF, in the future. There's a question in the chat that we'll go to. Thank you for the insightful talk. How many years were developing the site at Ludwigshafen? Was that the first site?
That was our first site, yeah. So that was where BASF was founded. So it's 1865. So that's what 158 years, if my math is right.
Okay, yeah. And how many products, following on from that, how many products flow out of that site?
That is our main site. So there's probably, trying to think, probably 5,000 products, probably 6,000 products from that one site, different products.
And they're all interlinked as well. So
it's fully interlinked. So you have the steam cracker at one end. So we have naphtha coming in one end, it gets broken to steam cracker. You have inorganics that come in along the Rhine, and it all gets fed together. So each production site is linked together where they need to be. And as I said, in terms of, so raw materials are going to one production site, that'll come out, maybe feed another production site, waste materials, and therefore where we have byproducts and we can't use them, we have our own waste to energy site as well. So we'll generate our own energy from waste that we produce.
That's phenomenal. It's really is quite a significant operation.
Yeah.
Okay. So have you ever changed, another question in the chat from Grace Lowe, have you ever changed a step at Ludwigshafen, and if so, how did you go about that?
Yeah, I mean, with great difficulty, in terms of, part of it is what do we require for a production process. So we have stopped production and moved it around. So it's about what do our customers need at the end of the day, is what do our customers require and how do we meet those requirements in that production site. So it's about building up those resilient processes. So it starts with the steam cracker, and everything then feeds from that in terms of where do we want. So you've got the ethylene propylene and the downstream products that we move into. So the monomers, the amines.
Right. Okay. I think we'll make this the final question, considering the time. So presumably you don't, and this has come from Kevin Hallas, so presumably you don't cool things to warm them up again at the next stage. Hard to do that at the proving stages of a new process.
That is, yeah. And part of that is how do we, when we're looking at those processes and scale up, to make sure in terms of, so if you develop something in research and you're moving to pilot scale, is then you have those production sites. So the pilot scales are fairly close to the production sites so that you can see where the issues are. So if we're developing, upgrading a new plant or using a raw material, actually you have to take into account, does it fit into our current existing process? And if not, how do we make it fit to our process? Because these are continuous, and that's always the challenge here, Tim. So as a production site manager, you've got two targets now. One is that CO2 reduction and raw material change, so bringing in raw materials. But on the other side, you've also got customers demanding product today, tomorrow, every day at the same quality. So how do you bring in new materials and also satisfy demand? So those production sites, they're continue looking for the raw material change, the new materials, and also trying to satisfy the customers on the outlet.
Yeah, I was going to say also that you must also have to satisfy the rise and fall in demand for different products at different times as well, which must be add an extra plate to spin.
Yeah. So then, and also that raw material. So in terms of, we've invested just over 2 billion in offshore wind to generate the electrons, and like Shell in terms of developing an electrolyzer to provide ammonia, green ammonia for our sites.
Yeah. Okay. Well, thank you very much, Darren. Thank you very much for an excellent talk, and I'm sure everybody will join with me in thanking you. A round of applause there from the Zoom meeting.
Thanks.
Okay, moving on to our final talk, and this is from Bhavin, and Bhavin is going to present on making chemicals from CO2, the future of electrochemical CO2 conversion.
Okay, can you see my screen?
Yes.
Okay, great. Okay, just give me a second. Right, okay, so today I'll be giving you an overview of this exciting technology on how to use electricity to convert CO2 back into valuable fuels and chemicals. But first, I just want to give an overview of the work that's being done at the center. So the center here is composed of academics from these 8 universities, and we work on a diverse areas with the overall goal of trying to achieve a more circular resource flow for the chemical industry. And we have research in different themes. For example, one theme is the fundamental technologies that will convert waste back into valuable chemicals. For example, we have a team working on biomass conversion, either to syngas or to other oils and chemicals. We have a team working on plastic conversion, where we take in waste plastics and put in with input of hydrogen and convert them back into their original monomers or bulk chemicals like liquid oils. And the next part, the third part, is electrochemical CO2 reduction, which I'll be talking about in more detail today. But apart from these, we also have teams looking at a more larger scale, say looking at process integration, life cycle assessment, how all these processes fit into the industrial processes, how do we optimize these systems, what are the costs, what are the environmental impacts. And finally, you also have a theme working on even the larger scale of policy, society, and finance. Today, the technology that I'm going to be talking about is electrochemical CO2 reduction. So here we've got CO2. It can either be captured from a concentrated source like industrial flue gas, or it can be directly captured from the air. And you have an input of energy. Hopefully it will be renewable electricity, and you feed it into a CO2 electrolyzer. Hopefully you make fuels and platform chemicals. And I'll go into the details in the next couple of slides. But first, I just want to note that all this will be available in the future because renewable electricity is becoming more and more cheaper and more available. So here on the left, I'm showing the cost of renewable electricity for 4 different technologies. And I'm showing that as compared to cost of making electricity from fossil fuels. And as you can see, in 2010, not too long ago, only 13 years ago, the cost of renewable electricity was so high that it wasn't competitive. But in this short span of just a little bit more than a decade, the cost has come down to be competitive, or even in some cases slightly cheaper than making electricity from fossil fuels. And on the right, I'm showing the annual capacity expansion. So the blue bars are the added renewable generation capacity each year, and the gray bars are the non-renewables. And the red is the percentage of those that are renewables. So for the last year, so this was actually slightly surprising to me, that more than 80% of new power generation is by renewables, and that's a very good thing. Okay, so if we've got plenty of renewable electricity, what kind of products can we make from electrochemical reduction of CO2? So here I'm showing a selection of products. So on the left, so we can make formic acid or carbon monoxide. So these are more simple to make. So these only take 2 electrons. And so they're more simple, and the technology is more developed. And as we move along, if we add 6 electrons, we can make methanol, 8 electrons, we can make methane, and these are a bit more complex to do. And then on the right, we have C2 products like ethylene and ethanol. And these take more electrons, but they're also more difficult because now you need to activate 2 molecules of CO2 and have them react together to form a CC bond. And all these are valuable bulk chemicals in the chemical industry. And mostly they're generated from fossil fuel sources at the moment. For example, if you look at carbon monoxide, which is part of syngas, now it's currently made from either coal or from methane steam reforming. Methanol is made from syngas, and ethylene is made from steam cracking. So it'll be really useful if we can replace all these processes with chemicals that are made from CO2. Okay, so what does a CO2 electrolyzer look like? I'm showing a diagram here. So there's 2 compartments. There's a cathode and there's an anode, and each side has a different catalyst that you need to put on to do the reaction. So on the cathode side, you feed in CO2 through these porous structures in the electrode, and then the catalyst would turn this into the reduced carbon products. But also, you also at the same time need a balancing reaction. In this case, it's usually water oxidation, and this is also the same technology that's used in water electrolyzers. Here I'm showing a picture of a cell actually from the lab. This is the actual one that I use. And so in the lab scale, we're working on these smaller scales, so say about 5 square centimeters. So it's the size of a postage stamp. So these are scales that we are working on, but hopefully we can find a way to translate into larger, say, square meter scale that will be needed in the industrial scale process. Okay, so I just want to give a quick overview of where we are now and where we want to be in terms of performance metrics. And here I'm comparing, rough numbers of the current best technologies to some targets. And I'm basing these targets based on some other mature electrochemical technologies like water electrolyzers. And there's different metrics you can look at. For example, there's the rate, which is measured at current density. And we can reach quite a relatively high number with the current best cells. And there's selectivity or Friedrich efficiency. What proportion of your input electrons is going into making your actual products? And depending on your catalyst, we can get really selective catalysts. For example, with silver, you can get more than 95% selective for CO. With tin, you can selectively make formate. And with copper, you can make up to 75% ethylene. And so for energy usage, you can look at the cell voltage or the energy efficiency. And so for cell voltage, the lower the better, right? This is the voltage you need to apply to get your cell to run. And in these areas, we still need to improve the cell voltage a bit. We want it ideally to be under 2 volts, and we want the energy efficiency ideally to be at least about 80%. And you can also look at the CO2 utilization, where how much of your input CO2 is actually going into your target products. And depending on the cell design, some of these CO2 can be lost as carbonates, which will require more energy to recover and regenerate. So this can vary wildly depending on the cell design. But ideally, we want CO2 loss to be close to zero, as close to zero as possible. And then the last bit, so I think the most challenging bit is the durability of the systems. So on the lab scale, usually, say in my own work, if I'm doing a standard run, I would do it for maybe like 3 or 5 hours, and that'll be a good amount. And for long runs, I would do maybe 100 or 200 hours. So 200 hours is like a week. And so for us on the lab scale, this is already quite long. And the longest that I've seen reported in the literature is about 3,000 hours. But if you're thinking about moving towards the industrial scale, where you need your actual processor to last for maybe 5 years or 10 years, we still have a long way to go. So 40,000 hours is about 5 years of continuous operation. Okay, so I want to introduce some research that is going on at the center here. So we have a team in Loughborough led by Professor Eileen Yu, and this work is done by Dr. Pritam Sharma, and they focus on designing new catalysts to control the selectivity. So here they investigated a mixture of copper and tin. So we know that if you start off with copper, pure copper, it makes a diverse mix of products. You get hydrogen, you get CO and other C2 products. And use it pure tin, you get mainly formic acid, right, with a bit of CO and hydrogen. But interestingly, if you mix the two together, make a copper tin alloy, the majority products become CO, which is neither the major products of in either of the pure metal cases, and it's quite interesting. And for more details, they've recently published this paper this year with more detailed characterization and measurement at different operating conditions. Here for my own work, I'm part of a research team at the University of Liverpool, led by Professor Alex Cowan. And here we're looking at a different facet of the problem. We're looking at cell design, designing cell to have low CO2 loss. And what I mean by that is, so with conventional cells that we are trying to replace, so they have these problems of that if you put in a certain amount of CO2, only a tiny amount is actually going to your carbon products. The majority is lost as carbonates or as crossover CO2. So we want to replace this. So we've designed a new cell using these bipolar membranes, and this will prevent any crossover or loss of CO2. And hopefully, so this will translate into higher yield of your target carbon products. And then for more details, you can check out these publications here. So the takeaway message I want to give is, so if you have CO2 and you have renewable electricity, you can use that to make valuable fuels and chemicals. And if we want to move to a larger scale, industrial scale, we need to think on different scales. We need to think from the smaller scale, designing different catalysts, and then designing the electrolyzer cells that the catalysts fit into, and finally design the overall processes where these electrolyzers can fit in. And for the different metrics that we're looking to improve, I think the key ones here that we definitely need to improve is the cell voltage, the CO2 utilization, and the durability of the systems. So for more information, not just on this part of the research, but other research that's been done in the center, please visit the website www.circular-chemical.org with more information. And thank you very much for your attention, and I'll be happy to answer any questions.
Thank you very much, Bhavin. Thanks for an excellent talk on an upcoming technology to deal with surplus CO2. There is a question in the chat. So what proportions from Grace Low, what proportion of cost of the overall system is the membrane for the systems you are currently investigating?
Yeah, I don't have the actual numbers on hand, but membranes are quite a pricey part of the system. And also, it's also a part where it's probably one of the easier parts to break down. And that's active research into this area, but there's different kinds of membranes or like cation exchange membranes, anion exchange membrane, bipolar membranes, or even replace them with like a solid separator, which is also a different kind of cell design. So yes, it is a big part of the capital cost.
I've got a question around, are there certain products, target products, which actually promote the formation of carbonate in this system?
Well,
so for example, if you're going for alkenes or formic acid, does one favor the promotion of carbonates over another?
It's not so much the products that are promoting this formation of the byproduct carbonate. It's rather with the cell design. So some cell design, when they choose to focus on a certain metric, say they want to increase selectivity, but at the same time that will come a cost. So for example, they need to use a highly alkaline environment, and that's mostly contributing to making the carbonates. So in some sense, if you focus too much on one metric, you are losing out on a different metric on CO2 utilization. So yeah, so that we need to a way to think about this in a more overall view.
Okay. Are there any more questions? I'm conscious of the time as we've hit our 1 o'clock mark. So if there are no more questions, I'd just like to wrap up this first webinar. I'd like to first of all to say thank you to the speakers for 3 excellent talks on the transition away from fossil fuels, and I'm sure everybody here at the webinar will join with me in thanking the speakers for their time. I just want to point out that please, if you've enjoyed this webinar, please keep your eyes open for our future webinars. There will be a series on this topic in the future, and we'll be continuing those next year. As it stands, thank you very much for coming along, and I hope to see you again at our future webinars. Thank you very much. Thanks to all.